So there's actually a good question. Someone asked, what if the current is going the wrong way in the Kirchhoff's loop that you're going around and analyzing in that Kirchhoff loop rule? Or if you don't actually know which way the current is going, like one of these examples. So I want to also record the solution for this and show you how do you analyze it if you don't know which way the current goes, okay? So the tip number 1 and 2, the first 2 steps of doing these is the same as before. Number 1 is make sure you label everything. And what you want to do is you want to label each resistor, give it an Ri, each battery, give it epsilon I, and each branch, give it I, like this. Okay, so for each branch, label the current, for each battery, label the epsilon, and each resistor, label its resistance like this. So in this diagram, you already have all the resistance labeled and the battery labeled, but you don't have the I labeled. So we want to label that as well. And I always want to redraw the diagram so that I have more space, and also it also allows me to think about and absorb to digest what the diagram really means and what the question really is asking for. Okay, so this question asks for to determine the magnitude and direction of the currents, right? So in each resistor. So what it's really asking for, you might want to state your aim as well. Okay, so you can redraw the diagram with these labels, and at the same time also state your aim. Okay, so the diagram we're concerned here is with the battery facing this way and a resistor here. So as you can see, I get a much more in-depth understanding of what the problem is asking, and also it gives me more space to label everything as I do this. So R1, R2, R3. So if I don't know which way the current goes, because this looks like the current goes up, right? This looks like the current goes down. What you want to do is make a guess first. Okay, so because for example, if this battery is extremely powerful and this is very, very weak, what's going to happen is the current is going to push it up here and going to basically override this battery and just going to push it through this way. So in this bottom branch, there's no telling which way the current actually goes. Does it actually go to the right or to the left? In this case, it most likely, if they're roughly of equal strength, actually, even if not, they're most likely both going to the right on the top and then on the middle going back. But you know, if I put another battery here, it could be different. Okay, so let me just show you the general case on how to deal with this. Is first you make a guess of which way the currents will go. Okay, so for example, now I'm just going to make a completely random guess and say that the current on this branch, on the top branch, is going this way, and then it's going to split up into I2 and I3 like this, right? So I'm going to just make a complete guess that I1 goes this way, I2 goes that way, and I3 goes that way downwards. And the relationship between that at this junction, as you can see, is I1 splitting up into I2 and I3. So now with common sense, you might think that most likely I3 is going the other way, but let's see what happens if you mislabel this. And it's completely fine. No matter how you label it, as long as you interpret your variables correctly, you'll get the correct answer. Okay, so it doesn't matter which way if your initial guess is correct or incorrect. You just need to know how to interpret what the number that you get out of it is. Right? If you get a positive sign, what does that mean? If it gets a negative sign, what does that mean? Okay. So what is the aim of this problem? Is it asks you to find the resistance, the currents going through each resistor. So I1 is the current going through R1, and coincidentally I've labeled it in, or this is simple enough that I2 corresponds to R2 and I3 corresponds to R3. But either way, as long as you have your branches, even if there's more resistors, you know that they're the same current along the branch. So if I have a fourth resistor over here, then this current will be the same over everywhere along the same branch for the current to flow in a steady way. Okay, so the aim over here is to find I1, I2, I3. That's my aim. Okay. So now we move on to thinking about Kirchhoff's rules. So first you decide on a loop. Like I said, I usually like to start with a battery and go around. So let's call that loop 1. Okay, and let's again for the second one, I like to start along with the battery direction. But let's say you decide to, so instead of going this way like this, you decide to go the other way around. That's also completely okay. Okay, so I'll show you what happens if you do this for the second loop. So it doesn't really follow along this battery. Okay, all right, so let's start with the easier one with loop 1. So let's write down the potential drop equation for here. And so you can draw a diagram if that makes it easier, but I'll just write down the potential drop equation directly once you get the hang of this. So first, you need to add up all the potential difference of each components along the way. So I first have the battery, I have this guy, and then I have this guy before I come back. So there's only 3 terms. It's relatively simple so far. So what's the potential difference for the first battery? It's going to provide, battery always provides a positive increase in the potential difference. So it's going to provide that. And now you hit a resistor, okay? So the next thing you hit a resistor. So the resistor always subtracts a certain amount of potential difference, right? So how much? Well, it will subtract I1 R1 amounts of potential difference. And as you go through here, this is the simple case, right? Everything is in the same direction as they are. So you're moving along this direction. The current is pretty much the same way as your loop is going. So you have this time it's I2 and R2 equals 0. Okay. All right, so that's very simple. That's a quick recap of how you would do it in the normal case. How about in the more complicated one over here? All right, so let's write down every piece first. So let's start with the battery, epsilon2. If I'm analyzing my loop around this way, so the next component I see is R2. And the next component I see is R3. Right, so adding all these should, by conservation of energy, they should go back to 0, right? All right, so what is the potential difference for this guy? Well, normally, a battery always provides a positive increase, but this is the wrong way round as I'm going around the loop, right? See, I'm analyzing in this direction. So instead of going from the shorter leg to the longer leg, I'm going from longer to shorter, right? So I need to flip this around. Excuse me. And so the extra minus sign, I put an extra minus sign over here to represent the fact that the battery is not facing the right way as my analysis is, okay? All right, so now I hit this guy, all right? So it's a resistor, so normally you do minus, but you see the current is, again, going the wrong way against my analysis. I'm analyzing it from left to right, so I'm trying to write down the potential drop in this direction. I'm trying to write down the potential drop in this direction, but the current is sort of going against the way that I'm analyzing it. So we need to account for that by putting an extra negative sign in front of I2, like that. Okay, so this extra minus sign, so the first minus sign is telling me that any resistor is going to cause a potential drop, right? But the current that my guess of my current is going this way, and it's opposite to how I am making which way is positive, which way is negative for my loop, right? So we account for that with the extra minus sign. Okay. And then we move on to this. Again, a resistor always subtracts. And what do we subtract here is I3 times R3. But this time it is in the right direction as I'm going this way, and I3 looks very smoothly going along the way that nature intends. So you just need I3R like this. Yep. All right. So there you go. So now we can try to check off things that we do know, and we're given epsilon1 is 9, epsilon2 we're given is 12, and R1, R2 is also given. That is actually R3. So the only unknowns here is I1 and I2, here is I2 and I3, but we also have this relationship over here, so we can plug that in. So first let's simplify the second equation a little bit. So we have minus epsilon2 plus I2 R2 minus I3 R3. So you see I have 3 equations, 3 unknowns. I can use this I1 equals I2, I3. I can plug it in here. So now it'll eliminate I1 completely. And I just have 2 equations and 2 unknowns. I can rearrange them and eliminate one of more and solve all the I's and get my A. Okay. Before I go into the deep algebra of things, let's see what happens if you made a different choice. If you made a choice to analyze the loop this way. So let's call that, so you go the other way around. Let's call that loop 3. How would that equation look? Let's start with the battery over here, right? So you have epsilon2 plus R3 plus R2 equals 0. So this guy, this time it is in the right direction, right? As my analysis, I'm going along this way. So this is going to be very natural. It's going to provide a boost in the potential difference. And now it goes over here. All right, so now R3, it's a resistor. So it's going to create a potential drop instead of a potential increase. However, the I3 is facing the wrong way, right? So I will get minus I3. I need to account for that extra minus sign. It's facing the other way. And then I move to here is another resistor, so I put a minus sign there. And this time it is facing the right way, so I can just write this down. So let me simplify this a little bit. So I have I3R3 minus I2R2 equals 0. And let me erase the positive sign in front over here. So this is the one, the green one is if I follow this direction. The red one is if I follow this direction. Look what happens. This is exactly the same thing as this. If I just multiply an overall minus sign, -1 to this, you see that this will become negative, and then this will become negative, which is this term, and this will become positive, which is this term. So you see, it does not matter which way you go around. You can do completely either way, as long as you follow the rules. What is the rules? The rules is this. If you see a battery, it's always going to be positive. Okay, so whenever you see a battery, look, even if it's the wrong way around, put a positive sign first. But if the battery is wrong way around, wrong way, okay, quote unquote wrong way, so it's not facing the way that you're analyzing the loop against, then you do negative epsilon of that. So this is how I like to do. I always separate out the two signs. I always put a positive anytime I see a battery first. That's the first thing I think of. The second thing I analyze if it's facing the right way. If it's facing the wrong way, I put a negative sign here. Okay? And for resistors, so if you see a resistor, the first thing you do is always negative. Okay, so just like over here, as long as when I follow the green one, as soon as I see the resistor, I just immediately put down the first negative. Okay, then I look at what happens to what is the right current I should put in, and the current that I made a guess is it's going this way, so I put a -3. Okay, so if the current is going the wrong way, account for that by doing a double negative in front of the I over there, like this, okay, or like this. So you see, every time I see a resistor, the rule is every time I see a resistor, I'm immediately putting in a first minus sign. And then if it's going the wrong way, if the current is pointing against my direction of analysis, so let's call this loop the direction of analysis, then we put an extra negative sign in front of it. Then if you follow these two rules, or these 4 rules over here, then you will always get it right, okay? Now, is the real current going in this way, right? I need to find the magnitude and the direction. The magnitude is just plugging all the numbers, but let's see what happens with it. How do I get the right direction out of this? So we need to actually do the math, so let's bear with us. I'm going to erase the second part over here. Or actually, let me start a new page. I will copy out the key formulas. So remember, these are the key formulas we have from our results. So this is from loop 1, this is from the red loop 2. So let's plug this in here to first eliminate I1, because remember, all the epsilons of the battery, the EMF of the battery are given, and the resistance of the resistors are all given. We just need to find out what the currents are. The current is the last thing we usually find. It's the most dependent thing on the battery and the appliances that you put in. Right? So you plug this in. And before it gets a little bit more abstract, so let's actually plug in the numbers. So what are we given? We're given that epsilon 1 is 9 and epsilon 2 is 12 in perfect SI units. And R1 is 25, R2 is 48 and 35. Okay, 25, 48, 35. So we can plug this in. So we get 9 minus I2. So you have 25 plus 48 minus 35, 0. And here we have minus 12 plus 2. Okay, so how do we solve a simultaneous equation? Well, just make one of them the subject and eliminate the rest. Sorry, this is R1 over here. Should be 25. Okay, so you can choose either way. Let's choose, let's eliminate I2. from here. So we can plug that into here, which will give. Okay, so we grind through the algebra and you solve for I3 and you got a negative number. What does that mean? So you got negative 0.12 amps like this. So we look at the diagram and we made an initial guess that the I3 is pointing downwards, right? But we got a negative number. So what does that mean? So you probably guessed that and you'll be right that it's actually going up instead. So I3 is, so that means that we actually made a wrong guess if you got the minus sign, but that's not a big deal. So you, as long as you know how to interpret it, then you will be able to know what it means. Okay, so at the end, you want to, how do you answer the question? You'll say the magnitude of I3 is 0.13 amps. You can write therefore it's 0.12 amps, and the direction is let's see what's the best way to write this. So the actual direction is going this way. Now that we know this was a wrong guess, it should be that way. So let's write it as counterclockwise. Okay, so I3, it's not good to write up or down because over here, the I3 is actually, so the real I3 is actually going up, right? And the real I3 is actually going down, here it's going to the right. I guess you can write right, but then here it's going up. So I guess the best way to write it, to explain the direction of the current through here is counterclockwise. Or actually, this question asks for the current through each resistor. So it's actually asking the current through this point. So I guess you can actually write it as up or down as well. So you can write it as it's going up through R3. So both is okay. So we can write the direction as either counterclockwise or up through R3. Okay. And then now we can plug that in to get I2 as well. And then once we have I3 and I2, we can get I1. Okay, I'll quickly do that as well. Okay, so for I2, you see that make sure you keep, because once you've defined I3 as going that way, even though in reality it is going the other way around, but you, in the mathematics, you already committed in that way. So do not plug, so make sure you keep whatever value negative signs you get, whether it's negative or positive, in the algebra, and then interpret it only after you get the results, okay? So that's why I keep the negative sign when I plug it in here. And so in the algebra, I'm committed with the direction already. Now that I got the answer, let's add in that human element, not just a machine calculation of the results. So this is the mechanical calculation, right? A computer in principle can do all these algebra, but now let's add in the human element to interpret this. It's a positive number. That means I have made a good guess. that the current is actually in fact going in this direction. So going through R2 has a magnitude of this much amps, and the direction is to the left, okay, through R2. Okay. If we actually started off and made, for example, if you made an educated guess and guessed that the I2 goes this way, go to the right instead, what happens is every I2 you see here will just differ from my I2 by a negative sign. So all your equations will be different. So this brings up a point that when you're doing your tests or exams or homework, make sure you label all your I1, I2, I3 on the diagram. So that's why this step over here, step 1 and step 2 is very important, redrawing the diagram and labeling the variables you use, because every single person taking the exam will probably make a different guess over here. There's no guarantee everyone will guess the variable goes this way. However, if you interpret your answer correctly, like I say from the beginning, someone else might get a positive, someone else might get a negative, but that's because the way they defined which way they start in their diagram. But the final answer, when I write therefore, whether it's going up or down, you should all agree on this at the very end if you interpret it correctly. Right? So if you do not define your variables, there's no way to grade whether your answers are right or wrong. So if you got the final right answer in a test or exam, maybe it will probably assume that you know what you're doing. But if you get the wrong answer at the end, so if you get a wrong magnitude or a wrong direction at the end, and if you do not have these labels over here, you will get 0 partial credit, because there's no way we know that whether you understand how to use Kirchhoff's rule or not, right? But if you label it, then we can actually see, oh, you actually got loop 1 correct, so maybe you'll get half the points, and you got loop 2 wrong, so you will probably lose the points over here. So you'll still get half the points for doing that right, or maybe it's just a minor algebra mistake that's just deducting 1 point out of 5 or something like that, okay? So that's very important, because when we reiterate is if you do not label your I1, I2, I3, there's no way to tell if you understand the concepts or not, and we cannot tell if you just randomly put in some I1, I2, I3 here, or did you actually understand most of the concept and you just screwed up one bit, and we can only deduct that part, right? So this is very, very crucial. Step 1 and step 2, do not skip defining your variables. Make sure there's no widow variables, no undefined variables, and all the variables that appear here are traceable, that we can see which way you defined your I3. So let's complete the last bit to add this up. This is very easy. Okay, so as you see, again, when I'm doing the algebra, I'm not interpreting it. I'm interpreting it after I get the algebra. So when in principle, I don't even need to do the interpretation here. I can just do all the algebra first and then do the interpretation, right? So while I'm doing the algebra, make sure you keep whatever minus signs you get when you plug it in, because you already committed on the first diagram, right? If you change it halfway, then you need to change all your equations if you want to change the direction of the arrow halfway through. So maybe one better way is you just grind through the algebra and get all the values first, and then do the interpretation on the last step. So that wouldn't, there will be less chance to screw that up. So make sure you understand that. So the last bit here is the I1, the magnitude is 0.04 amps. And through resistor 1, which way is it going? So that means I got a positive number. That means my initial educated guess is pretty correct. So it's going this way. So it's going to the right off. So direction equals to right through R1. Okay, all right. Hope that is clear. And let me know if you have any questions. And that's it.